All right, we're picking up with chapter 11 on chemical reactions. This video is going to go kind of quick, so again, feel free to pause. All right, so first thing, we're going to talk about how we describe chemical reactions and chemical change. And if you remember, chemical change is when something changes its identity, okay? So unlike physical changes, which just change the state, this changes the identity of the substance. So we use word equations. We have reactants on this one side and products on the other, separated by an arrow, and this arrow means yields, so reactants yield products. So here's some examples of some word equations. We have iron plus oxygen give us iron 3 oxide, or hydrogen plus hydrogen peroxide, when it breaks down, gives us water and oxygen. So jot a couple of those down in your notes so that you know what I'm talking about when I say a word equation. Evidence of a chemical change. So you might remember we talked about this back in the early chapters, but we're going to quick go over it again because it's going to come into play, especially when we go in lab. How do we tell that something is changing, that its identity is changing, a chemical reaction is happening? One, release of heat or light. So if we see something start on fire, we know it's a chemical change. If we touch a test tube and it feels warm, it's probably a chemical change, or cold even, it's usually a chemical change. Production of a gas. So if we add two things together and we see bubbling, okay, this usually means bubbling. I'm going to move this over so you can see the picture. Okay, so if bubbling starts to happen, that's usually a chemical change. Not boiling, that's where we'd see water molecules changing into gas molecules, but bubbling as in a new gas being formed. Formation of a precipitate. So a precipitate is an insoluble solid, and we saw this in our lab where we did the little the little drops. So we have two clear solutions, notice. When they hit each other, they react and form this fluffy yellow precipitate. It's an insoluble solid, so it will not dissolve in water. And the last one, a color change. So we see this color change happening. If there's a color change, then usually that's a chemical reaction. We see a color change here. The match is going to a black color. Here we get a bright yellow substance. Okay, those are all chemical changes. Again, I'm going to go fast, so feel free to pause. All right, some things about chemical equations. We separate our reactants and products using an arrow. Here's an example of a chemical equation. It's not balanced yet, but we'll get there. And we use labels to indicate what state everything is in. Okay, so is it solid, liquid, or gas? So here's the major ones. We know solids, we're going to show an S. Liquids, we use a little L, and gas, we use a G. And we'd put those right here, and you'll see that in the next couple problems. The last one that you're not familiar with probably is aqueous. Now, this is important in chemical equations. Aqueous, just like it sounds, aqua meaning water, means it's dissolved in water. Okay, and that's not a bad idea to jot down here, dissolved in water. We use an AQ to abbreviate that. Now, remember, aqueous is not the same as liquid. Liquid means we've melted that substance down, but aqueous means that we've just dissolved it. So salt, it would take a lot of heat to melt it, but we could easily dissolve it in water. Okay, so balancing equations. When we want to balance equations, we have to go by this rule. The law of conservation of mass states that whatever goes into a reaction must come out. The mass of the reactant must equal the mass of the product. So what goes into the reaction has to come out, whether it comes out as a gas, as a solid, or in some other form. For example here, if we count, let's see if this is balanced. We're going to count these atoms. So I have one carbon here, and I have one carbon on this side. Whatever's on the reactant side has to be on the product side as well. It doesn't have to be in the same form. It can be bonded with something else, but they have to be there. So one carbon, and we have two hydrogen on this side. We have two hydrogen on this side. We have two oxygen here, and we have 1, 2, 3 oxygen total on this side. Okay, so is this balanced? The answer is no. It is not balanced. We'd have to do some balancing. Okay, so let's talk about how do we balance if it's not balanced? And the answer is we use coefficients. These are placed in front of the symbol. Okay, and if there's no coefficient, you can assume there's a 1 there. So remember, what goes in must come out. So we're going to do an example here. So here's iron plus oxygen gas gives us iron oxide, iron 3 oxide technically. And I'm going to go ahead and change to my pointer. So what we want to do is first count. So I have 1 iron here, and I have 2 iron here. So what I'm going to do is I'm going to write them down. Okay, I'll give you specific orders here in a second to write down. I'm going to draw a line between my reactants and my products. So iron on this side and oxygen on this side. So whatever's on this side is going to be also on the other side. So right now I have 1 iron, so just put a 1 next to it. I have 2 iron over here, so I know I'm not balanced. I have 2 oxygen on this side, and I have 3 oxygen on this side. All right, so time to balance. Let's start with our iron. We want 2 over here, so I'm going to put a coefficient. This is a coefficient here. So now I have 2 iron. Okay. Now I have 2 oxygen here and 3 over here. So the first place these are going to meet, I can't multiply it by 2, that would just be 4. I'm going to multiply this one by 3 and this one by 2. So now 3 times 2 gives me 6 oxygen on this side. 2 times 3 gives me 6 oxygen on this side. So what I'm doing on the bottom is just keeping track. I'm just keeping a tally. Because I added this here, now I have to say 2 times 2 means now that I have 4 iron. But that's okay, I can just go back and change this here. So instead of 2, I'm going to put a 4 here. Now I have 4 iron on this side, 4 on this side, 6 oxygen and 6 oxygen, so I'm balanced. So it's kind of like a seesaw. You go back and forth until you got it balanced, okay? Now this 4, 3, and 2 are my coefficients, okay? So here's a little definition for coefficients for you. They represent the number of units of each substance. So again, we saw coefficients. I like this picture down here because it shows you an actual representation of the atoms. So this is CH4. And if you notice, there's nothing here. So there's 1. So this is 1 molecule. It's a carbon and 4 hydrogen. Here we have 2 O2 molecules, so here's 1 molecule of O2, here's another molecule of O2. We have 1 CO2 molecule, so we have 1 CO2 molecule, and we have 2 H2O molecules. Now notice, if we went through and counted, we'd find that the products do in fact match the reactants. So we have 1, 2, 3, 4 hydrogen over here, and we have 1, 2, 3, 4 hydrogen over here. Now they're not in the same form, they're bonded differently, but they're still there. Here we have 1, 2, 3, 4 oxygens, and 1, 2, 3, 4 oxygens over here. Okay, then lastly we have 1 carbon here and 1 carbon here, so we are balanced. Okay, just gives you an idea of why we have to keep track of these and why we use coefficients. Okay. Oops, sorry, 1 second. All right, some rules for balancing chemical equations. Only whole numbers are used, so we're never going to use halves or fractions. Coefficients are always going to be whole numbers. Once written, the subscripts cannot be changed. You can't change any subscripts. Number of each element must be the same on the reactant side and on the product side, so you can't change it. What goes in must come out. Element symbols cannot be added or deleted from an equation. And lastly, the simplest whole number ratio for coefficients. So if it's 2, 2, 2, we'd have to reduce it. Okay, and I'll give you plenty of examples in class. All right, here's our order, the order in which we're going to balance equations. We're going to go metals, polyatomic ions, nonmetals, hydrogens, and then oxygens. Okay, you don't have to do it in this order, but it makes it nice and easy because hydrogen and oxygen tend to be the hardest to balance, so we like to keep those for last. Some things to know, common diatomic molecules, remember di means 2, these are elements that bond with themselves when they have nothing else to bond with. And that'll come into play a little bit later, but jot these down. You can highlight them on your periodic table as well. Let's do some practice. So the first thing you want to do with these, and I'm going to choose a different ink color here. Let's do green. All right, so the first thing you want to do is count your atoms. So I'm going to draw a line. I'm going to separate my reactants from my products, and I'm going to write everything down in the order that I want to do them. So remember, you start with metals. So I have lead here, and I have sulfur, and I have oxygen. So I'm going to start with lead, and then the next, I'm going to go to sulfur. It's a nonmetal, and I'm going to save oxygen for the last. Same thing, I should have the same elements on my product side, because whatever goes in must come out. Okay, then I'm going to count. So I have 1 lead on this side, and I have 1 sulfur, and I have 2 oxygens. Okay, same thing here. 1 lead, 1 sulfur, but I have 1, 2, 3 oxygens. So I'm not balanced. Oops, why did I rewrite that? Sorry. I'm not balanced, so I need to balance. My lead and my sulfur are good, so I have to jump right to oxygen. I have 2 here. I have 2 here, and I have a third here. So what I'm going to do is put a 2 here. Okay, that way I'm going to make an even number that I can multiply by on the other side. So now for oxygens, I get 2 from this compound and 2 from this compound, so I have a total of 4. Lead now has 2. Okay, we put a 2 here. Okay, so now I'm going to go balance my oxygens out. Now if I have 4 oxygen here, I can simply put a 2 here. 2 times 2 is going to give me 4 on this side. And now I notice my lead is out of whack, so I have 2 on my product side, so I have to add a 2 here. All right, but now because I have a 2 here, my sulfur is also out of whack. And then so I have to go back, look at sulfur, I have 2 and 1, put a 2 here. Now I have 2 on this side, but look, oh, my oxygens are out of whack again. So 2 times 2 is 4, plus 2, I now have 6. So that means I got to go back. I can change this to a 3. Now 3 times 2 is going to give me 6. So I see 2 matches, 2 matches, and 6. So I'm balanced. All right, so it can sometimes be a back and forth, kind of like a seesaw. Sometimes it'll be one letter you just plop in there, and sometimes it's going to be a back and forth. So don't get discouraged, just keep going. Let's try another one. So again, I'm going to write it out. You don't have to write it out. I like to because it keeps track. When you get really good at these, I'm fine if you don't want to write them out. Okay. So I'm going to go with potassium first. I have 1 potassium, 1 potassium. I have 2 hydrogens on this side, and I have 1, 2, 3. Oops, not 2. I have 3. 3 on this. That's bad. Here's 3 on this side. Oxygens. I have 1 oxygen here, and I have 1 oxygen here. So close, but not quite balanced yet. So potassium are good. Now I go to hydrogen. We have 2 here and 3 here. Closest place those are going to come together is 6. So put a 3 here. This makes my hydrogen 6. And now my oxygen is 2. Then I'm going to put a 3. Nope. So I did it again. So if we look, I forgot I had this extra one here. I'm actually going to put a 2 here. That's going to make my life easier. So forget I did this. Okay. If I do that, then now I'm going to have 2 and 2 and 4 hydrogens now. Okay, then I can just go back here and put a 2 here. Now that'll make my hydrogens 4, my oxygens 2, and if I notice, okay, my oxygens and my hydrogens are good, the last thing I'm going to need to do is add a 2 here to balance it. So sorry, I should have picked a little bit easier ones. Let's do one more, and I swear this one will be the easiest. Oh, and of course, it's slightly too big.